Howdy folks, welcome back to some review. We're going to do some review on Boyle's, Charles, and the combined gas law. My hope for us today is that if you take a look at this video, it's going to be helpful and kind of insightful on why we use specific types of units here and why, in this case, we see Boyle's law differently than Charles' law. I do see some discrepancy happening between those two laws, and a lot of us are kind of getting some stuff mixed up in this case. You know, when I see that some students are working with Charles' law, they're not putting opposite sides of temperatures on the other side of the equation. They're just keeping it the way you see it, and that's not how we do that. Let's go through them both, and hopefully we'll kind of correct our errors here. So, with Boyle's law, as the pressure of a gas increases, the volume has to decrease. This relationship between the pressure and volume is called inverse. Now, how can we tell that from the equation? Well, if you take a look here, the pressure 1 is next to P1. And if they're next to each other on the same side of the equation, that's going to be an inverse relationship. If they were on opposite sides of the equation, that would be a direct relationship. But in this case now, one has to go up while the other has to go down. It's like that equilibrium. If you increase something, something has to decrease as a result. And think of this in terms of the world and how we kind of work with this. You know, if a balloon goes up into the atmosphere, it's going to decrease the pressure because there's less particles pushing on the atmosphere the higher you go up. What's going to happen to that gas? Well, the gas is going to be more free. They're going to expand because they're not as burdened by the pressure. And so they're going to expand and expand and expand until that balloon eventually pops. Now for a graph, it's going to look a little bit like an asymptotic curve, like it's going to kind of curve downwards. And that's what your graph is going to look like. Now let's do an example here, and then we're going to do one on Charles and one on combined gas law, and hopefully that'll make sense for everybody. So it says some chlorine gas occupies 250 milliliters when its pressure is 720 millimeters mercury. What volume will it occupy when its pressure is 750 millimeters mercury? All right, so at this point we all know we have to use this equation, Boyle's law. We got a few things here. We know the first pressure and the first volume. We know the second pressure, but we don't know the second volume. So, very simply put, we just put them all together into this equation. And we'll notice that we have V2 as an unknown variable. To get it by its own side, we just divide by 750 on both sides. And it's going to look a little bit like this, right? 250 times 720 divided by 750. That's going to give you just V2 on its own side. And if you do all the math correctly, your answer is going to be 240 milliliters. Now, units. How can we look at the units this way? Well, we have millimeters mercury divided by millimeters mercury, and they cancel out. And so what's going to be left is just volume in milliliters. Now, in this case, we're just going to keep it the way it is. For Boyle's law, for Charles' law, for the combined gas law, whatever you see for units, you're going to keep it the way it is. You're not going to change it. That, however, changes when we go to the ideal gas law. And the reason why is because now we have a universal constant. This constant tells us a lot about what we have for the units. I would highly recommend watching my homework number 5 full guide and clarification video here for an in-depth analysis on why that has to be specific units and the entire answers, or all the answers to number 5 for the homework, and my process of going through them. So I'd recommend watching that for an in-depth guide and for a great review so you can become more prepared for the test that's coming up. Alright, so let's go back to Charles' law here now. As the volume of a gas increases, the temperature has to increase. This relationship is called a direct. Now, how can we tell it's direct? Well, as we see here, the first temperature is opposite to the first volume. and the second temperature is opposite to the second volume. If you see that in an equation, it's going to be a direct relationship. Because now what's going to happen is that as you increase the volume, the temperature has to increase on the same side, on the opposite side, I mean. Or if you decrease the temperature of the second, you're going to have to decrease the volume of the second. And so that's going to be a relationship that we can see very clearly in this law, and for your graph is going to look like a straight line. Now, don't forget we always have to use Kelvin. We can't use degrees Celsius. And at this point, we all should know that degrees Celsius, we just have to immediately convert to Kelvin at this point, right? So like negative 65 degrees Celsius here is going to be 208 Kelvin. Well, how do I find it to 208 Kelvin? I just add 273 to negative 65, right? For 37 degrees Celsius, I add 273 to 37. Now, if I am in Kelvin and that wants the answer in degrees Celsius, well, then we have to convert backwards. We have to subtract 273. However, I've given you a leg up in that case, and there's going to be no questions on the test where you have to convert backwards. Just plainly, if there's going to be an answer in terms of Kelvin, you're going to have to find that answer and make it as Kelvin. So, let's go through number 6 on Charles' law. Given 152.2 milliliters of methane at 87 degrees Celsius, at what temperature will the volume be 145 milliliters? Okay. V1T2 equals V2T1. We know that we have 3 of the 4 total variables. So we have V1, T1, V2, but no T2. And so I'm going to plug it into our equation as we see here. Right, V1 is going to be with T2, V2 is going to be with T1, and you should see this occurring. Don't forget, we have to add 273 to 87 degrees Celsius to make it 360 Kelvin. And some people may ask questions like, why do we have to do that? Well, think about it like this. Can we have negative numbers for an equation? Can we have a negative volume for our equation? And the answer is no. We can't have a negative volume. We have to have some specific volume that has to be positive all the time. And so that's why we have to keep it as Kelvin, because Kelvin doesn't have negative units. It all has positive. The lowest number is going to be 0 Kelvin. Alrighty. So we plug it into our equation, we isolate T2 on its own side, which means we have to divide 152.2 on the right side. It's going to isolate it by itself, and now it's going to be 343 Kelvin. And if you wanted to find out that answer in degrees Celsius, all you do is take that and you subtract 273 from 343. And let's do that right now. You're going to be in answers of 70 degrees Celsius. And so that's how you find your answer in degrees Celsius if they ask you that. Alrighty, we're flying by. Let's do one on the combined gas law. Now, combined gas law, don't forget there's a lot of variables to consider here. V1 P1 T2 equals V2 P2 T1. Now, it's like what we have for Boyle's law, right? V1 P1's on the same side. However, for Charles' law, T2 is different. It's on the opposite side than V2. And so we're going to see that for our equation here. V1 P1 is going to be on the same side, but T2 is opposite to V2. And so that's how this equation was made. So it says 0.00837 liters of nitrogen dioxide is collected at 57 degrees Celsius and 932 millimeters mercury. At what temperature will a gas occupy 0.224 liters if the pressure is 46.1 millimeters mercury? Alrighty, we got a lot of information there. Now don't forget Kelvin, right? We have all the information we have here. All we got to do is plug it into our equation, and since all the units match up, we're going to keep it the way it is. It's going to look a little bit like this. And to isolate T2 on its own side, I would have to divide these two units, and now they're going to be below on the right side. It's going to look a little bit like that, right? Your answer is going to look like 439 Kelvin. So that's going to be your answer for this problem. Again, if you see a lot of variables on a test or on a question for like this, most likely you're going to have to use this equation. Now, how do I differentiate between this equation and, let's say, like the ideal gas law, which deals with also a pressure, volume, and temperature? Well, here's what I find as kind of key points to differentiate or kind of find the difference between the two. If you see two volume amounts, you're going to have to use the ideal gas law. Sorry, you have to use the combined gas law. If you find that the answer or a question has mole amounts or some gram amount, you're going to have to use the ideal gas law. And so if you see two of any unit, like 932, 46.1, you're not going to use the ideal gas law at this point, right? Liters and liters, if you have two volumes, you're not going to use the ideal gas law. However, if you find that you have some moles and also a volume and pressure or temperature, then you have to use the ideal gas law. Alrighty, so take a look at my other video. Don't forget about this. This one's going to be a great help for you. And then I have some help on homeworks number 4 and 5. If you have any questions, please let me know, and have a great day.